In this section, we shall look at error sanctioning, or better still, losses. And coming back to this previous schematic, our aim is to actually make sure that the difference between each of these points, say this point for example, and the function we're going to be dealing with is minimized. So we want that whatever function we choose to represent our data set should be as close as possible to the data points. So in this case, if we're choosing this, then, or say we're choosing this, then for this particular point we have this distance from here to this, whereas for this other line the distance is from here to here, which is not very different. And then if we let's take this other line for example, we have this error that's from this point to this line, we have this error, whereas from this point to this other line we also have this other error. Now notice that if this point made up all of our data set, then it's clear that this other line is the best fit for our data set. So in a nutshell, we're trying to choose or select a function based on certain parameters or weights and biases such that these differences are minimized. One of the most popular loss functions or error sanctioning functions is the mean square error. With the mean square error, we take for all I going from 1 to m, where m is the size of the data set, so this m represents each row for our data set. So if we have a data set like this one, this m represents the value 6. So for all I from 1 to m, that is for this, and this, we want to have, or we want to subtract the predicted value based on our model, which we have described already, minus the actual value, which is the target value. So in this case, for example, we have this as our target value, and then our model is going to give us a predicted value. Now, knowing fully well our model has this parameters theta 0, which is the bias, theta 1, the weights, theta 2, theta 3, up to theta n. So we're supposing that we have n different inputs, although in this case n equals 2 because we have just these 2 inputs. So in this case we should be talking about theta 0 plus theta 1 x1 plus theta 2 x2. So since our output or y I predicted is gotten by a linear combination of the weights and the inputs, we have this, which is this, minus the y I target, all of the squared, hence the term mean square error, because we're squaring here. And then the mean comes from the fact that we're dividing all through by m. So if we have 1,000 data points, we're going to divide all through by 1,000. Now, this mean square error, being a quadratic function, takes this kind of shape. So let's look at this example concretely and see how with this mean square error we're able to calculate its value using this data set. So in this case, for example, we have theta 0 plus theta 1 times 73 plus theta 2 times 12 minus, so we have all this here, minus 13.2, because 13.2 is the actual MAC, that's y I target. So in this case I is equals 1, so we have y1 predicted, which is this, minus y1 target, which is this. So given a triplet of values, say theta 0, theta 1, theta 2, so if we have two triplets and we want to compare which is actually best for our model, we'll simply have to input them here. So we have theta 0, this. If you input this and you calculate the error and it's less than another triplet of theta 0, theta 1, theta 2, then the first model is best placed to represent our data set. Another example of a loss function is the mean absolute error. In this case, we have, instead of squaring y predicted minus y target, we have y predicted minus y target absolute value, hence the term mean absolute error. And here we divide by m again. So we have this, And then recalling that the absolute value of x is equals x if x is positive and negative x if x is negative, we have this kind of function. Now, these two losses actually have some shortcomings. For the mean square error, suppose we have an outlier. Now, what's an outlier? An outlier basically in this particular example would be that student who has a very low quiz mark, a very low class R value, and then a very high mark. So suppose here we have 2, year 2, and then year 20. That's going to be an outlier because that's not very common. But the problem which arises is that when we're trying to sanction our model for making errors, we tend to look at outliers the same way we look at normal values like this one. And what still, since the gap between the outliers and the predicted function is generally going to be very large, the error is going to be squared, which is going to produce an even larger value. So the mean square error has a shortcoming at this level. For the mean absolute error, we shall first talk a little bit about training, although we're going to work with it subsequently. Here, generally when doing training, if we are at this point initially, we're simply trying to make sure we get to this point where we have minimal error, although that's not always the case in practice. So in this case, if we're here, we always wanted to get to this point where we have the minimum error. Now, what is good about the mean square error is that as we approach this minimum error, we tend to take smaller steps as the gradient is actually reducing. So if we're at this point, we take this large step, at this point a smaller step, and up to the minimum value. Whereas here we tend to take very large steps, and these very large steps may make it very difficult to train such models. Apart from that, the mean square error is also easier to work with as compared to the mean absolute error because of this absolute sign. Now, there is a middle loss, or a loss which takes into consideration the advantages of the two and actually brings that forward for us to make use of it. So in this case, we have the Uber loss. For the Uber loss, we have this for every I. So we suppose we are working with an I. Yeah, we're not going to use a summation sign because each of the I's has a different value. So here we have for every I, although at the end of the day we're going to be adding actually. So every I we have yi predicted minus yi target all squared if the absolute value is less than a certain threshold set to. So if we have a certain threshold, what we're simply saying here is if what we have, or if the value we're dealing with isn't, or if the inputs we're working with aren't outliers, then let's use the mean square error, because here if the y predicted minus y target is not very different, or if the difference is not that much, like in this case where we have this absolute value which is less than a given threshold, then we're going to use this mean square error. But in the case where this is greater than that threshold, that is, we suppose that we're dealing with an outlier, then we're going to use the modified version of the mean absolute error, which happens to be tau of the absolute value of y predicted, or yi predicted minus yi target, minus half of tau squared. So that's it for the Uber loss. Now, depending on your problem, there is a loss which is going to be best fit. So for linear regression problems, the mean square error loss, mean absolute error, or Huber loss are kind of one of the best losses or loss functions we could use. And dealing with classification problems, we tend to use different kinds of loss or other losses apart from these three losses we've presented already. Now, let's suppose that we have the probability of having y equals 1 given inputs x and certain parameters theta. It should be noted that we're now working with a classification task, so we're not working with this anymore. Now we're saying whether a student has passed or failed simply. So when we say y equals 1 in this case, we're kind of saying when the probability of status being equals 1, or status or probability of a student passing, and when y equals 0 is the probability of the student failing, given that we have the input and the weights and biases. So to better understand the notion of conditional probability is important for you to go through our probability course. Now we could define this probability as a function y pred, which varies with respect to theta and x, and yeah, the probability of the student failing given the inputs and theta being equals 1 minus y pred. So we're gonna develop a probability distribution which kind of summarizes these two initial statements. Now, summarizing these two, we're gonna have the probability of yi. So in this case, the probability that we have a 1, it could be a 1, it could be a 0, given the inputs xi and the theta. Note that here we don't have theta I because theta is theta. Theta doesn't vary with the different data points, because basically theta is our weights. So we have this is equals yi pred of theta x to the power of yi target. So we have this, which is what we had up here, to the power of yi target. The only difference now is that we have included an I. So yeah, we have I pred. And all of this times 1 minus yi pred of theta x, all of this to the power of 1 minus yi target. Now, this may look a bit confusing, but let's take a simple example. So suppose we have yi equals 1. So if this y, so what this probability distribution does is when yi is equals 1, that is when our target is equals 1, and given this xi theta, here we should have this as 1. So we're kind of taking this example. So we're taking this case, that's when the y target is 1, because this y is the target. So when yi here is equals 1, obviously here we have 1, so we have yi pred to the power of 1, and here we have 1 minus yi pred to the power of 1 minus 1, and this is going to have 1 minus yi pred to the power of 0. So this term is removed and we're left with yi pred of theta x, which gives us this. Now when yi equals 0, so when we are having a target 0, we have yi target 0. So in this case, this we have yi pred to the power of 0, which is 1, and we're left with 1 minus yi pred to the power of 1. So we have this. And if we were to repeat this for the m different data points, in this case m equals 6, we'll have a probability distribution defined as such: p of y given x and theta equals the product of yi pred to the power of yi target times yi pred to the power times 1 minus yi pred to the power of 1 minus yi target. That's multiplying all these terms together from I equals 1 to m. In probability theory, we have the concept of maximum likelihood estimation, wherein we try to get the best possible parameters theta, which will ensure that when given inputs x, our distribution will give us outputs which will be similar to the targeted outputs. So in this case, we'll be wanting values of theta such that the probability of having y as a target, of having y equals 1 as target, or having y target to be equals 1 will give us a value of 1. And hence in this case, the probability of having a y target as 0 will give us a value of 1 minus 1. So here we're going to have 0. Generally, instead of working with the maximum likelihood estimates, we tend to work with the maximum log likelihood estimates. And we should see the reason why we prefer the log likelihood estimates. These log likelihood estimates are generally more stable as compared to the maximum likelihood estimates themselves. So we prefer to use them, and also they are also easier to work with. But then two conditions actually make them the right candidate for the maximum likelihood estimation task. That is, for all x greater than 0, the log of x is continuous, and for x greater than 0, the log of x is increasing. So we have here a monotonous function for all x greater than 0. And from these two conditions, we could say that y is bijective for all x greater than 0. So in this sense, maximizing x, that is maximizing this value of x, is going to be similar to maximizing log of x, because as x increases, the log of x too increases, and as x decreases, the log of x decreases. Let's rephrase our maximum likelihood estimation problem. So here we're finding the best possible theta given our input x, which will give us a density function which maximizes the likelihood or similarity between this output and the target output. So we can rewrite this as argmax of log p, or probability of y given x theta, with x and theta as parameters. And that's because the maximum likelihood estimation is the same as using the maximum log likelihood estimation. And with this, we have this writing. We can also say that instead of maximizing the log likelihood, we could minimize the negative log likelihood. So we have this, which is same as having argmean of negative log of the probability of y given x theta. Let's take some log rules. The log of a times b is equals the log of a plus the log of b. And the log of b to the power of c is equal to c log of b. And with this, we derive the binary cross entropy loss, which is equals -1 on m. The negative is actually from this, so we're trying to minimize this loss. -1 on m, the sum from I equals 1 to m of yi target times the log of yi predicted, plus 1 minus yi target times the log of 1 minus yi predicted. Now, you may be a bit confused of where this formula comes from. Actually, we've basically replaced this p, or this probability of y given x theta, by what we had initially seen here. So we've taken all of this and we've replaced here. Now, these are actually products. So we are having y1 pred to the power of y1 target into 1 minus y1 pred to the power of 1 minus y1 target times y2 pred, y2, 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 up to, let's say in this case, y6. So we're actually having these products, and it's kind of like the a times b times c times whatever value we have. So log of ab is equals log of a plus log of b. Log of abc is log of a plus log of b plus log of c. So the log of these products is simply the sum of the logs of each of them. So it's just like in this case, we had the log of a, b, which is the sum of the log of a and b. So we have log a plus log b. In this case, we have the sum of log this. So in this case, we have this like our a. So we have yi pred to the power of yi target like a, and then 1 minus yi pred to the power of 1 minus yi target like b. So this represents our b. So we have log of ab. This is a product. We have log of ab to be log of a plus log of b. That's why we have this log of yi pred to the power of yi target plus log of 1 minus yi pred to the power of 1 minus yi target. But log of b to the power of c is equal to c log b. So this powers here actually comes this way. That's why instead of having yi pred to the power of yi target, as we saw here, we instead have yi pred yi target times the log of yi pred, and here 1 minus yi target times the log of 1 minus yi pred. And then for these products we keep on having here is replaced by this summation sign, and we've seen that already with this rule. Nonetheless, as we had seen under the section on modeling, for our classification tasks, or in this case binary classification tags, because we just have two classes, hence the term binary, we have y I pred or y I predicted, which is the sigmoid of the theta 0 plus theta 1 x1 up to theta n xn. So that's actually y I pred, which is this. We add this little epsilon in case we're working with computers or we're writing a program, because in case we have the sigmoid of this giving us 0, we won't want to have an error, since the log of 0 is going to throw an error. So we just add this epsilon to account for that. Now similarly here we have the same, we have log of 1 minus sigmoid of this, and that's as we've seen already on the modeling, that the output is gotten by taking theta 0 plus theta 1 times this plus theta 2 times this, and getting all of that and finding the sigmoid of that to have our predicted value. So that's why we have the sigmoid of this here, and basically that's how we derive our binary cross entropy loss. Now the reason for the term entropy actually comes from information theory. Generally in information theory, supposing we have 2 bits entering into a system, so we have 1 bit which comes in, the first bit, suppose we have the first bit 1 and then the next bit 0. Like in this case we have this, say we have this 1 0. The entropy kind of characterizes or tells us whether there's been a gain of information or not. So if initially you had a 1 bit entering into the system and then it switches up to a 0, that's much gain of information, because initially we didn't have this 0. So in that case our information is kind of considerable. But if we had initially 1 and then later on we have a 1, the system sees that there has been no change of bit, and so there is no new information which is passed. So since our entropy characterizes the amount of information in the system or the amount of new information in the system, we tend to give this loss the name binary cross entropy loss, as is having similar characteristics with this loss function we're trying to calculate. Now let's get back to the loss function. Suppose we have y pred equals 0 and y target equals 1. Let's put this as inputs and see what we get as loss. So here we have y pred 0, we replace here, we have this 0, and then here we have a 1. So we have 1 times log of 0 plus 1 minus y target is 1, so we have 0. So we have 0 times log of 1 minus 0. So in this case our final answer is going to be y target times log of y predicted, because this part is already 0. Now our y predicted is 1 is 0, so we have 1 times log 0. Now log 0 is like, from looking from this curve, as x tends towards 0, because log 0 doesn't actually exist, we could only work with limits. As x tends towards 0, this y function is tending towards negative infinity, so we're going towards negative infinity. So log of 0 we could say is negative infinity, and with this negative sign here gives us positive infinity. So we find that once our target is 1 and our predicted value is 0, our loss increases, that turns to positive infinity. So this actually tells us how good this loss is, because it kind of sanctions our model whenever the target is 1 and the predicted is 0. Now if the predicted is 1 and the target is 0, we have a similar situation where, for example, if here we have target 1, so here we have 1, no, here we have target 0, sorry, here we have target 0, so if you have 0, all of this term is off, and here we have 0, so we have 1 times log of 1 minus 1, which is log 0. Negative infinity times this negative gives us a very large number, so it kind of sanctions our model for giving us this kind of output. The next, if we have y pred 0.1 and y target 0, Firstly, our y target is 0, so in this case we're gonna have 0 times whatever we have here as a 0 plus, then here we have 1 minus target. Our target is 0, so we have 1 minus 0, which is 1. So here we have 1 times the log of 1 minus 0.1, because our y pred is 0.1. Now log of 0.9 is kind of almost log of 1, and we know that log of 1 is actually 0. So this point here is actually where we have x equals 1. Since log of 1 is 0, log of 0.9 should be almost 0, although not actually exactly 0. It's going to give us kind of a negative value, which is almost 0. And the negative value times this negative here gives us a positive value. So we find that whenever our model predicts y to be 0.1 when the target is 0, it is kind of not very much sanctioned because it's almost the right answer. Now, if our y pred is 1 and y target is 1, so in this case we already see that this term goes away because y target is 1, so we don't have to do with this term, and then we're working only with this one. Now our y target is 1, so we have 1 times log of y predicted, which is 1. Log of 1 obviously is 0, so we have negative 1 times 0, which is 0. So our loss is exactly 0, and we see clearly here that every time we kind of predict the same answers, our loss goes to 0. Now looking at this, you may have thought that working with this kind of task, we would have maybe used the mean square error. But then if you look at the mean square error here for this case, we have a loss of 1, that's 0 minus 1, that's 0 minus 1, which is 1. 1 square is 1. Whereas here we had a loss of almost like a very big loss, that's actually infinity, that's positive infinity. So we see that this binary cross entropy loss kind of knows how to sanction very well a model whenever it goes astray. Now other loss functions actually exist, and the importance of selecting an appropriate loss function cannot be overemphasized, as is basically these loss functions which permit us to know whether we're in the right direction or not.